right. I've been recording a lot of interview prep videos lately, trying to help folks pass their coding interviews, and felt like I should take a break and instead talk about a probability question. It's very unlikely this will come up as interview prep. I don't know that the audience for one is the audience for the other. But I found this really interesting and just wanted to share it with folks. This was brought to my attention by a young friend of mine who I have the pleasure of tutoring every once in a while. Tutoring is probably rounding up. He's a very brilliant individual, and I don't know that I help all that much, but sometimes it's helpful to have someone around you can bounce answers off of or bounce questions off of. So he brought this problem to me and wasn't really sure how to approach it. Probability problems are hard in general. I taught at Texas A&M for a few semesters. I taught freshman business majors a survey course in mathematics, and that included a probability and statistics portion of the class, and that was never... Well, there's a lot of stories there, and maybe I'll tell those some other time. Right now, let's talk about this probability question. And one of the things I find very interesting about this one is that when I initially answered it, I got it very wrong. And a funny thing about probability questions is that I feel like that happens a lot. They're just always a little bit surprising, and they're always a little bit counterintuitive. So we'll talk about the wrong solution I had, and then we'll talk about the right one. So the problem is this: you have a fair coin, you're going to start flipping it. This coin has two sides, heads and tails, and you're going to start flipping it until you get either tails, heads, heads, tails, or heads, tails, heads, heads. And the question is, what's the probability you get the first before the second? So a lot of times when you see these before kinds of questions, they wind up being very independent events, and therefore you can approach it just as a intersection problem and move on. This one is a little bit different because that tails, heads, heads shows up at the beginning of our win condition and the end of our lose condition. And so when I was first thinking about this, I was like, well, okay, there's two cases. The first case is that we get it in the first four flips. We flip immediately tails, heads, heads, tails. Right? So probability that we get tails, heads, heads, tails, well, that's just a probability of a half 4 times. And so that's just 1/16. So that's the first case. The first case is we get it in the first 4 flips. The second case is we don't get it in the first 4 flips. We get it some other time. Well then, okay, really what's happening here is we have to include what happens right before our success condition. In other words, it's not just that we get tails, heads, heads, tails. It's that we get tails, tails, heads, heads, tails. Given that we get tails, heads, heads, tails, 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 heads, heads, tails, or I'm going to just put a plus here, our failure criteria, heads, tails, heads, 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 and heads, tails, heads, heads, tails. Now, the first reaction might be, well, wait, why are you throwing in the heads and the tails at the end of our failure? We already failed. Why would you keep flipping? And the reason you would keep flipping is it's just going to be a lot easier to understand how these things intersect if we make them all the same length. Right? Because now we can say, hey, there are 3 possible ways for us to stop flipping. Right? And they all have these, they're these 5 flip sequences. And if we get one of those 3 5-flip sequences, we win. And if we get one of the other 2 5-flip sequences, then we lose. And otherwise, we just keep flipping until we get one of those 3. So that's just 1/3. And so then my claim is, that's the probability if we kept going. But why would we have kept going in our first 4 flips? Well, we couldn't have won by getting tails, heads, heads, tails. And we couldn't have lost by getting heads, tails, heads, heads. So this is times the probability we had to flip more, which equals 1/3 times 14/16. There are 14 other ways for us to keep flipping after, that will require us to keep going from those first 4 flips, right? One could win, one could lose. We have 14 other ways, and so we have to multiply by 14 over 16. That's going to give us 14 over 48. And then it's just 2 cases, so we're just going to add those together. We get 1/16 plus 14 48, which is 17 48. And I'm like, cool, we're done. And he goes, I happen to know the answer, and I happen to know that's not the right answer. Huh. Well, okay. That's unfortunate. And so we were looking at it, and he goes, well, so the problem is there's some crossover in those first 4 flips, right? So in other words, if you didn't get tails, heads, head, tails in the first 4 flips, and you didn't get heads, tails, heads, heads in the first flip, but you instead got heads, 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 you've got a head start. Sorry for the pun. You got a head start on failing, right? Because you have a heads going into the 5th flip. So we've actually, so in other words, we need to consider sort of the carryover, and we aren't considering that here, which is an excellent point. So how do we consider that carryover? Well, we solved it a different way than this. And while I think there's value, there was a lot of, is this right, along the way? And it turns out it was, but it wasn't necessarily obvious to either one of us that we were on the right track. So I have a new way of solving this that is still based on what we discovered while we continue to work on it. But let's talk about what we really want here. We want THHT before HTHH. Now I'm going to, just so that we have a shorthand for this, I'm just going to say that S is success. S is winning, right? And winning is THHT before HTHH. And what we're looking for is, what is the probability of success? Now, in the concept of probability, there's this concept called given. And it's I guess the formal name for it is conditional probability. But the point here is you can be given information, and that might change your idea of what the probability is. So in this particular case, you might talk about the probability of success given, and we indicate that with a vertical bar with a pipe. So it's success given we rolled 8 heads. Rolled. I'm going to do that a lot. I'm just going to admit it. Look, a coin is just a D2. So in theory, you're rolling a coin and it comes up heads or tails. In the same way you might roll a D6 and it comes up, 3 or 2. Even if you don't buy that tough, I'm going to keep saying rolling, and there's just kind of no way around it. I don't know why I do that. Because rolling a coin is a different... Anyway, it doesn't matter. The point is, moving on. If you had the last, 9? The last 9 flips were heads. That doesn't matter. Right? The probability that you succeed, given the last 9 flips were all heads, is the exact same probability that you succeed given that the last one was a heads. In other words, the only thing that can count towards THHT or HTHH is the last H. And it's one step towards failing. Right? All these other H's, they don't matter. So what we can think about is, hey, can we answer this question by sort of memoizing the history of our flips? by remembering just the flips that contribute to success or failure as we move forward. So here's what that would look like. So what we want to do is find the probability of success. And my claim is that that's the same as the probability that we the probability that we flip a heads times the probability that we succeed given that we flipped a heads. And that's the same as the probability of plus the probability of tails times the probability of success given the tail. So in other words, the probability of success is just, did we get a heads? Cool, remember that and keep trying to succeed. Or did we get a tails? Cool, remember that and keep trying to succeed. And this is the exact same as the probability of succeed given heads divided by 2 plus the probability of success given tails divided by 2. Again, we're flipping a fair coin, so this shouldn't be too surprising. Okay, cool. Well, what's the probability of succeeding given that we know we have a heads in our most recent flip was a heads? Well, that's the probability that we flip a heads and given heads and the probability of tails times the probability of success given heads tails. In other words, you flip the coin again and see what comes up. So we know that this is again P of success given heads divided by 2 plus P of success given heads tails, again divided by 2. I forgot my divide by 2. Well, that's interesting, sort of. Except we just talked about having a whole bunch of heads in a row, right? Because the only part of the memo that matters is whether or not it contributes to our soon to happen success or soon to happen failure. Well, HH isn't at the beginning of either one of these flip sequences. So the probability that we have HH, we don't care about the first of those two H's. We just care about the second. So this is the same as, sorry, you gotta go like that. That means that P of S given H is the same as P of S given H divided by 2 plus P of S given HT divided by 2, because HT is getting us sort of down this path, this HT path. Well, wait, we've got a PS given H on both sides. So that means we can subtract this from both sides, move it over here. That'll give us the silly PS given. I do want to mention, because I just think these folks are great, that I'm using Lucid just to be able to type with big fonts. Could I have used anything? Yeah, Notepad or anything else? Sure. I like showing off Lucid. This is not sponsored. I can't imagine a world where Lucid would sponsor me. But I think they're fantastic. I love showing them off. Yeah, this is Lucid. So what we've just discovered is that P of S given H equals P of S given HT. In other words, and this is his insight, not mine, the probability that we succeed given the heads is the same as the probability that we succeed given the heads tails. In other words, you just keep flipping heads until you flip a tails. And nothing changes, right? You can heads, tails. You're eventually going to, is that true? Yes. You're eventually going to flip a tails, and as soon as you do, you are now that much closer to the failure condition. But it's just eventually going to happen. So the probability doesn't change going from heads to heads tails. So that means this equation that we came up with up here for the probability of success, we could just change this probability of success given H to success given HT. Isn't that crazy? When we started seeing this, we're just like, wait, this doesn't make sense at all. Well, we're just going to remember for now that the probability of S given H is the same as the probability of S given HT, and keep going. The reason we're going to do that is because the probability of it, spoiler, the probability of S given H is just going to show up 20 times. So we'll just remember for a second that this is how things are working. Okay. The next thing is S given T. And again, I can write all of this out, but we just know it's going to be probability of heads given probability of heads added to the memo, or times probability of heads of success given heads added to the memo, and the probability of tails times the probability of success given tails is added to the memo. And heads and tails, they're always going to be divided by 2. So I'm gonna stop writing the probability of heads and probability of tails part and just divide by 2 every time. So this is the same as the probability of success given tails heads divided by 2 plus the probability of success given tails tails divided by 2. All right. So again, the probability of tails tails doesn't start either one of our success criteria. So this is the exact same as the probability of success given tails heads divided by 2 plus the probability of success given tails divided by 2. And again, we have success given tails on both sides of the equation. So we can subtract it out and wind up with P given ST divided by 2 equals P S given TH divided by 2. And so again, we wind up with P of ST equals P of STH, which is so crazy, I think. But again, this is how it all boils down. This is how it all shakes out. And again, it's because this TH, once you flip tails, and tails is the only thing in your memo. Remember, this is important. Tails is the only thing in our memo here. So that means whatever happened before tails, we could throw away safely. So, but the probability of the only thing in your memo is tails is the exact same as the probability that the only thing that you've added an H to that memo, because you just keep flipping tails until you wind up with a heads. So fantastic. Okay, we're going to keep going. So the point is, we don't have to keep answering things we don't have, right? So we don't have to worry about probability of S given TT because we haven't recorded that anywhere. So we do have the probability of S given HT. And again, we're just going to add in a heads or add in a tails, and then we're going to add that to the memo. So this is now just the probability of success given HT, H divided by 2 plus the probability of success given HTT divided by 2. All right. And so now, again, we use this to say, hey, does anything look like this in our success criteria? Yeah, sure enough, heads, tails, heads is the start of our failure condition. So this is an important memo. But heads, tails, tails is not the start. Okay, so we lose the H, right? You drop the first, the oldest thing off your memo. And now we say, okay, what about TT? No, that doesn't start anything. Okay, now we lose the next T. And so we're left with this last T here at the end as our probability. So this is the probability of S given HT equals the probability of S given HTH divided by 2 plus the probability of S given T divided by 2. Well, we know S given T is the same as TH. We haven't done that one yet, but that's fine. Let's just hold on to the fact that this is the same. Does that make sense? In other words, we know that S given T is just S given TH. S given TH is closer to something valuable to us. So I think that's more valuable than holding on to this S of T. So we're going to chop that off. And this is now going to become our new H of T. All right, so now let's answer P of S given TH. And again, we do the exact same thing. It's now becoming sort of mechanical. We're just going to add in a heads to the first and the tails to the second, and then go look at our flips and see if either of these line up. So is THH, Is that starting something valuable to us? Yeah, it sure is. That's the first 3 of the 4 for winning. So that's super cool. We'll keep him around. What about THT? THT does not start either one of these sequences. Okay, so we drop the T. Does HT start either of our sequences? Sure does. So this is the probability of S given THH divided by 2 plus the probability of S given HT divided by 2. So let's take just a second and look at what we've got here. Because it's this guy is referring to this one, and this guy is referring to this one, right? In other words, we have the probability of HT on here, which is this guy, and we have the probability of TH, which is this guy. Let's hop back to the thing that we kind of care about up here. And look at what this actually winds up being sort of in practice. Right? Because I think that'll be a little bit... Actually, you know what? Let's not do that. These are shorter to write. Let's just stick with that. Let's resolve this not as TH and HT, but as H and T. I think that's useful. Let's try that. So HT is really just H. So this guy, HT, is the same as the probability given H, and this is the same as the probability given T. Is that what we want to do? Man, I don't know. It's hard to decide. You know what? Let's just keep going for a second and see how all this sort of shakes out. And not try to do any substitution-y things yet. We know that these things are tautologically the same, and so we can go back and forth between these two however we need to, when we need to. Let's keep going forwards. Remember, I do want to point out, this is not the way we solved it. so I'm kind of just guessing at how this is all going to pan out. But that's okay. We've got HTHH. That's another one of the things we are aware of being. This is the same as the probability of S given HTHH divided by 2 plus the probability of S given HTHT divided by 2. And so we look at this. HTHH is our failure condition. The probability that we succeed. Remember, our success is we get THHT before we get HTHH. This probability is 0. We can't win if we've lost. So this is 0. Then we say, what is the probability of success given HTHT? Well, HTHT is not either one of these things, so we can just drop the H. THT is not any of these things, so we can drop the T. HT is the start of this guy. So this is the same as the probability of S given HT divided by 2. Because this was 0, so divided by 2, it's still 0. And this one, we drop this HT because the only thing that matters now is the fact that the most recent 2 flips were HT. So we just learned that the probability of HTH equals the probability of HT divided by 2. So crazy, isn't it? Let's keep going. So we really only have one more now. Success given THH divided by 2. Or I'm sorry, not divided by 2. Probability of THH is the probability of success given THHH divided by 2 plus probability of success given THHT divided by 2. THHT is our success criteria. So the probability that we win, given that we won, is 1. This probability right here is 1. We won, given that we won, then we won. The answer is we won. Yes, 1. THH. All right, well, that doesn't look like either of our sequences, so then we look at HHH, because we dropped the T. Well, HHH, we already know, that's just probability of H. So this is actually the same as probability of success given H divided by 2 plus 1/2. This is going to be awful trying to zoom around and stuff. That probably just made some people dizzy. But that's okay. We're almost done. Okay? So, let's collapse this down. So we now know how to sort of substitute back into these guys above. So we know HTH, which is this one, is the same as the probability of HT divided by 2. So let's replace this guy. So this is going to equal the probability of success given HT divided by 2 plus probability of success given TH divided by 2. Well, we know that HT divided by 2, this is just 4, so we'll switch that. And so we now know that the probability of HT given HT, and we can drop this, we don't need HTH anymore. We've replaced everywhere the HTH showed up. But we now know the probability of HT divided by 4 is the same as, wait, the HT's over here. So we can subtract that like we did before. So this is 3/4 times the probability of success given HT, because we subtracted a fourth from both sides, equals the probability of success given TH divided by 2. We can multiply by 2 on both sides. That gives us 3/2 over here. And so then we can divide by 3/2, which means multiplying by 2/3, and that gives us 2/3 times the probability of TH. Isn't this nuts? All right, hold on. We got this THH. We want to replace that in here. So this is now the same as, sorry. I know that's going to frustrate some folks, but that's fine. So we're going to plug in the probability of THH that we calculated down here. So this is the probability of S given H divided by 2 plus 1/2. All of that divided by 2 plus the probability of S given HT divided by 2. So that's, we've already plugged this in. We're going to delete him just to give us some room. So just to multiply that all out, it's probability of S given TH equals the probability of S given H. We're going to bring that divided by 2 is going to be a divided by 4 plus 1/4 plus the probability of S given HT divided by 2. All right. So that we've just simplified that guy. Well, is it simplified? Let's keep looking at this. We know that the probability of HT is the same as the probability of H. So this is just the probability of H, or S given H, and this was the probability of S given H. So wait, this is the same as the probability of S given H divided by 4 plus 1/4 plus the probability of S given H divided by 2. Well, we can add those two together, and so this is 3/4 times the probability of S given H. Oh, we've got to divide it. Hold on. We've got to divide it by 4 hanging out in an awkward place. I put the fraction up here on this one, so I'll put the fraction here on this one. Okay, so now we can scooch this back. Well, wait, hold on. The probability of HT is the same as the probability, 2/3 times the probability of TH. So 2/3 of this quantity is the probability of HT. So that's 2/3 of, this is getting crazy, isn't it? 3/4. It'll be all right. We'll make it. Times the probability of S given H plus 1/4. Well, we know that if we multiply the 2/3 by the 3/4, we wind up with 1/2. Stop. I don't need the formula library. I need to keep typing. All right. So 2/3 times 3/4 is 1/2. The 3's cancel out, and the 2/4 becomes 1/2. So this is 1/2 times the probability, well, the way we've been writing that before is the probability of S given H divided by 2. And then we've got 1/4 times 2/3. That's 1/6. Right? 1/4 times 2/3 is 2/12, which is 1/6. So what we just discovered is the probability of HT equals that. Well, now we know that the probability of heads equals this of S given H. The probability of S given H is that. And the probability of S given TH is that. But we know that probability of TH is the same as tails, and probability of HT is the same as heads. So that means in our original equation, this is the same as heads, this is the same as tails. And so what we wind up with is the probability of S is going to equal, hopefully this isn't skipping too many steps, but we're going to just do probability of S given H divided by 2 plus 1/6, that whole quantity divided by 2 plus the probability. You know what? Wait. Hold on. This is erasing some of the funness of it. So let's not go that route. Instead, let's say, hey, the probability of HT, this is the probability of H. This right here, I can cut that, and paste it right here. Right? That's the joy of saying that's the probability of HT. But now we've got the probability of S given H on both sides. So we do the same trick we did before. Probability of S given H divided by 2, because we're subtracting 1/2 from both sides, or 1/2 of that quantity from both sides, and that's going to give us 1/6. Now we can multiply by 2 on both sides. That gets rid of that 2 and turns this into 1/3. We just found out that the probability that we succeed, given that the most important recent result is a heads, and we can forget anything else that happened before that, the only memo we need is heads, is 1/3. Okay, well, we now know that this is TH, so we can just literally put it up there. This is the same as TH. Well, we know the probability of S given H is 1/3. This is just 1/3. We know that 3/4 times 1/3 is 1/4. We know that 1/4 plus 1/4 is 1/2. So if you come up here and you put 1/3 in for this and 1/2 in for this, you wind up with the probability of, this is so nuts to me. It's so hard for me to believe that this even happens. The probability of success is 1/3 divided by 2 plus 1/2 divided by 2, which equals 1/6 plus 1/4. If you add those up, you got to multiply. So we're going to wind up with 2/12 plus 3/12 equals 5/12. And that is the answer. Isn't that mind-numbingly crazy pants that it absolutely works out this way? I really like this problem. It is very rare for me to like a probability problem because I just feel like they never make sense. And this one had insights along the way where it was like, oh, okay, well, the simple thing makes sense. I guess getting to the point where you say the probability that this happens before this, given that we rolled a heads, flipped, given that we flipped a heads is 1/3. Like, that is crazy to me. And I have no idea how to come up with that except to go through the analysis we just did. I feel like this, because do you remember back when I was showing the first result we got? There was a 1/3 floating around. There was also a 1/2 floating around. So weirdly, for reasons I don't understand, had I not said, oh yeah, you have to multiply by 14/16, we would have gotten the right answer in completely the wrong way. Because we would have added 1/2 plus 1/3 and gotten 5/12, which is the answer. Well, I guess we would have had to divide by 2 somewhere in there. Would I have known to divide? But that's my point. Like, I don't understand even what it's amazing to me. I love this problem. I don't understand how this is the answer, but it's definitely the answer. This is the right answer. Isn't that crazy? I hope you enjoyed this. I still find it fascinating, having now solved it 3 different ways. And I hope you did too. Yeah. Enjoy.